we want the source cells to do it
Try just
Yeah, there should be an open force field group folder that they could go in. I can make sure you're done.
I think I as far as finding them again. Sometimes
Yeah, I agree.
Slack history gets.
That's what I was gonna do with them if. Yeah.
I didn't. Oh, you're gonna do it.
No, if you could do that, that would be great.
Okay. I was pulling the PDFs off to put with my own notes.
I'm just going to give a brief update on what we're doing in terms of the experimental stuff. So what building new host systems to be able to develop new HostGuest Binding data. So the host molecules that we're working on in terms of the synthetic development, in case you're not aware, is Cyclodextrins. If you've never seen Cyclodextrins before, they have a hydrophobic center where they bind drug molecules, a number of different molecules, and like Neil said, they're quite loose binders. They have a variety of guest molecule fit in there. There's 3 types of cyclodextrins. The alpha, beta, gamma. So it's 6, 7. Sorry, I can't see it. 6, 7, or 8. Oh yeah, thank you. So it's either 6, 7, or 8 monomers. We're focusing mainly on the beta cyclodextrin, which is the 7, because they tend to be more useful in terms of binding. But as you can see here, they have a bit of a fault, which is the fact that they are much less aqueous soluble than any others. So I'm hoping to be able to try and improve that as well. So in terms of what our final aim is going to be, it's going to be to try and take this. Ooh, dude. Fell down a hole.
Good thing you didn't back up.
It's going well.
That's right. You finally got somebody. Waiting the whole
Someone
time.
put it there on purpose.
That's right.
Yeah, so what we're trying to do is substitute onto the secondary phase, which is the larger rim, which is nice in terms of being able to get a variety of binding. But as I'll speak about in a second, it is also synthetically far more complicated to add onto the secondary phase, which is why there isn't as much out there in the literature. But what we're trying to basically do, the general idea is to make a number of different host molecules based on the cyclodextrins to be able to bind to loads of guest molecules and basically make a big library of host guest binding data. So just so everyone's kind of on the same page, in terms of synthetic challenges of cyclodextrins, they're great binding host molecules. They're not very nice to work with synthetically. So just so you can understand where the complications might arise and what we're trying to work around. Again, this is the cyclodextrin phase. We're looking at binding, adding a monosubstituent on the secondary phase. So you have, as you imagine, a number of hydroxyl groups. So we want one, because a lot of the cyclodextrins out there have random substitution, which is obviously not very helpful for you guys. But we also want to be able to understand how the binding's working. So the main thing we want to do is retain or ideally improve the aqueous solubility of the beta cyclodextrins. Otherwise, they're not really of much use. We want to prevent aggregation because cyclodextrins are known to aggregate, and if you were to put on a substituent on the side that would also aggregate, something like aromatic that might pi stack, you're going to get aggregates, and that's also not something that you want because you're not going to get that nice one-to-one binding that we're hoping for. So we need to be a little bit careful with that.
How does the aggregation work in the first place?
In terms of just cyclodextrin,
Yes.
I think Neil might have a better. They don't. I don't think they like cyclodextrin cells don't tend to
Like
aggregate.
the orientation you're talking about, it's usually like if here's the cup, then a neighboring one sort of like partially fills
Oh.
inside the cup.
Yeah, they. From
it's
what I've
kind
seen,
of like a perpendicular back and forth.
Interesting.
yeah, I've seen a few different ones of it, but that seems to be the most common. But obviously, as soon as you add on a substituent, like if you added on a naphthyl group or a benzene group of some sort, then you add in more complications. So we need to make sure we're not getting any aggregation. The main problem with synthesis is to monosubstitute that secondary phase. The primary phase is far more reactive, less sterically hindered, because it has one hydroxyl group for every 2 on the secondary phase. So we made it really easy for ourselves. But we've come up with a few. So these are the proposed routes we have so far that every one of them now is actually working, and they all work in a way in which there's a number of different starting reagents, so you can use the same reaction scheme, make a number of different derivatives that will have different types of functional groups on there. So for example, you can have this thiourea, so thioureas are useful anyway, but you can change that R group to be a whole host of different things. So it's an easy coupling reaction that will give you a wide range of substituents. And again, so the other one is the cyclic anhydrides, which is these. So it's going to give you this amide group. Obviously, amides are incredibly useful. The other one is, and this is one of the real aims, is to get the peptides attached to the side of the cyclodextrin, so you can actually get interactions with amino acids. So build the amino acid and then build the peptide off it, or build the peptide and then attach it to the rim. What it looks like at the moment is attach one and then put some sort of tripeptide on there. And the last one is the urea. So we've got the thiourea and urea ones, because obviously they're both useful binding.
And you just use the aminated form as a starting
Oh yeah, sorry, I didn't mention that. So thankfully, we could make this one. It would take us a while. Thankfully, this is commercially available. So we're starting from a slightly easier standpoint than making it ourselves, which is nice. But this does not necessarily react like you would expect an amine to react. As soon as you attach it to a cyclodextrin, it starts to do different things. Yeah, so it's a nice starting point to get that mono substitution. Saves an awful lot of time. And I didn't mention that's actually on the 3 position, so looking at 3 modified. We will look into the 2 modification as well, but at the moment I'm just focusing on this one. So at the moment, these are these beta cyclodextrin derivatives we have that are pure. And the reactions are working. They're all working in over 80% yields now, which is nice. So obviously we need a fair amount to be able to do ITC data, NMR data, so it's nice to have some good yields to be able to do that. And obviously purifying cyclodextrins is the other problem, but it seems to be going okay at the moment. So we have 3 of those cyclic anhydrides that I talked about. So you can see this is the R group here that we're modifying. So we've got the alkane, the alkene, and then we've got that aromatic group on there. Because it seems to be, because that one's so close to the rim, it doesn't aggregate, which is nice. And we have an aromatic without reducing the solubility. Because what we really need is to make sure we keep in those hydrogen bonding groups somewhere to retain the aqueous solubility. These ones actually have all shown solubility greater than 100 mg per mil. Beta cyclodextrin itself is only about 18 mg per mil, which is nice. And this one here, so you've got the thiourea, another thiourea with the furan group on here. Shows some nice binding properties. The urea. And then this is the glycine attached. We finally got the glycine molecule attached. And then we're working at the moment on building off the glycine. So I tried adding different amino acids instead of the glycine, but you have steric effects. Glycine is the only one that will directly add on to the cyclodextrin at the moment.
So the neutral ones, what's the effect on their solubility? The lower left 3.
All of these have proven to be more soluble than beta cyclodextrin.
Wow.
Native beta cyclodextrin. They don't appear to have this same massive increase in solubility as those. But when I talk about solubility, just to make it clear, I did do solubility testing with this. We have an instrument called the Sirius T3. It will do pKa values and a few other things in solubility. These things are so soluble in comparison to drug molecules that you need a lot to do that. So at the moment, I'm really talking about putting it into sort of a small 100 milligrams into a mil, and it all goes into solution, which is why I'm saying it's more than that. But all of these are definitely improved. These I've got 50 milligrams so far into solution, but obviously I don't want to just use up all my sample by doing this.
It's almost a little surprising because they've got a lot of non-polar surface area added on.
Yeah.
The glycine derivative also should be cation. Is it much more soluble as well?
Yeah, it's surprisingly, again, nowhere near as soluble as these ones, but still aqueous soluble and still more soluble than beta cyclodextrin. The easiest way to find out is I do the NMR when I do this in the same concentration as beta cyclodextrin. It takes a little while to get beta cyclodextrin in. These ones go in without any help at all. So that's a nice way of showing they are definitely all more soluble than the native one, without having to use any extra sample to do it. We have looked at alpha cyclodextrin as well, partly because alpha cyclodextrin starts off being much more soluble than beta cyclodextrin. So one of the reasons for doing it is if we found a number of derivatives where I have added something on to beta cyclodextrin and then it becomes insoluble. So we think, okay, well the reaction works, so why don't we use an alpha cyclodextrin and give ourselves another host molecule? A few of those aren't purified. I've only put them on here if they're purified and they can actually be used at the moment. But you can see we've managed to make the same cyclic anhydrides on the alpha. No problem with solubility, unsurprisingly. And then this reaction, which I am planning on doing the beta cyclodextrin, which I haven't got around to, is actually this one attached to lysine. So we've shown that we can actually do the coupling reaction off this one, and there's no problems doing it from there. By having it ever so slightly further away, we reduce the steric effects of trying to directly add the bulky amino acids on. And this one, again, is water-soluble. When it's attached to beta-cyclodextrin, I couldn't say for definite. We'll find out. But yeah, it's working quite nicely, actually. But obviously, we're hoping to expand much more for all of these. This is just an interesting phenomenon, I suppose, in terms of cyclodextrin binding, if anybody's interested, is that the thiourea reaction actually started off like this. So a thiourea reaction should be a 1-to-1 reaction, nice and simple, should take about 2 hours in high yields for a normal compound. When I did it, we had to add 3-to-1 equivalent of the reacting reagent to cyclodextrin, heat it more than you should, add more base than you should, and get a very bad yield. So I kind of thought, so what I figured is this is probably acting as a guest molecule. So it seems to be that you get about a 2-to-1 ratio of the cyclodextrin to that guest molecule, and then the third one reacts, but the reaction still isn't progressing very far. So what I did is I put adamantane inside cyclodextrin, and then did the reaction in the 1-to-1, and we got 80% yields. In a 1-to-1 ratio of the, much easier to purify, the adamantane comes out really nicely at the end, and you get much. So this could be a nice way around if we have problems with things binding inside. It also shows how the competition between guest molecules can completely turn into chemistry or something.
They don't have adamantane functionalized beads that you could like literally do the reaction on these beads.
We actually had that conversation, and we were hoping to use it for purification.
Yeah, exactly, right?
Yeah.
Just do it on the bead.
And I'm still looking into that, because I was hoping to get like a C18 column that's like capped with
exactly.
adamantane. Yeah, if you know anybody that's making them, that would be really helpful. Because I haven't found one yet. But the problem is, because I want something inert, because I don't want it to react, usually you cap something and you'd have sort of an NH2. I don't want any sort of reactive group on there, which is why I haven't managed to find one that's working yet. But yeah, this was quite a nice, just shows HostGuest Binding in action. I'm just going to show you a binding study that we've done all the way through with one of these to show you that by modifying it, we do still get the HostGuest Binding. So this is the cytinic anhydride that I've been talking about, and this is romantidine hydrochloride. For those that don't know, there's a lot of literature on any type of adamantane group binding inside cyclodextrin. But Sam had already found that this one in particular binds really nicely inside the native beta-cyclodextrin. So you can see here we've got massively improved solubility, which makes ITC much easier to do. You don't have any solubility limitations. We've got PK of 3.35, which is nice. We can actually measure the experimental for this, which will be really helpful. And no aggregation. At the end, I'll show you how we know there's no aggregation, because we've got quite a nice NMR experiment for that. For NMR binding for the substituted cyclodextrin, one thing to be aware of is if you've ever seen an NMR for non-substituted cyclodextrin, it does not look as messy as this. So as soon as you break the symmetry of cyclodextrin, you increase the number of peaks by about 7-fold, which means it's very hard to quantitatively track the chemical shift of binding. So I'm really using it just to prove we definitely have binding, but at the moment not quantifying doing it. But you can see that this group here is slightly off and it does shift. But again, I'm trying not to quantify with it because we can use ITC, which is much nicer. But it proves we definitely have binding. This is, like you talked about before, you have the NOSI data. So NOSI NMR is where you can look at intermolecular interactions that are through space. So I want to point out this was not calculated on, this is me just making an image based on NOSI data. So what we can see, which is really nice, and we can actually do this in phosphate buffer, which is what I've done everything in, rather than just D2O. So actually you can keep the same matrix with just 10% D2O, because obviously you know that as soon as you start changing the solvent system, you can change binding. So we've managed to set up a saturation of whole sequence that works really nicely. So you can see here we actually show secondary phase binding, because what we have is this group here with this group here. So you're actually showing binding occurring between the guest molecule and the substituent that we've added onto cyclodextrin, which is allowing us to get secondary phase binding. Interestingly, if you just have the amine group here, just the substitution of starting material, you get primary phase binding, which we assume is due to the repulsion of the two charge groups. So it's nice to show we can actually show directed binding.
Are the peak volumes sufficiently well integratable that we could be quantitative about the
NOEs?
The NOEs,
We've actually been talking about this quite a lot, and the problem is because if you see here, because we can't say for definite which peaks these are within the cavity, whether they're 2, 4,
Yeah,
or
there's
anything
no
like that,
specific assignment.
there's no way of sort of saying, oh, okay, well, it definitely isn't binding in a primary orientation, because ideally we want to see an NOE around here. What we actually have is an NOE for the entire cavity.
Mm-hmm.
So we were looking at the idea, and Neil in particular was helping me look at the idea of seeing if we could prove primary binding, but all we can do at the moment is prove secondary binding and say we don't know if it's also primary binding because of the complexity of this. So at the moment I don't know a way around that because there's no way of saying, okay, that's definitely the C6.
Yeah,
prediction.
and our
So,
chemical
yeah,
shift prediction is not enough to...
Unfortunately not. But we can prove we definitely have secondary binding. We have these cross peaks here that show there's definitely some binding going on here.
Does the fact that you've got NOEs all around the cavity tell you that it's spinning?
Oh.
Because your NOE, like just as you depicted it, you'd have a strong or medium short range, you'd have a strong range interaction just on the one side.
Mm-hmm.
So if you're getting it around the other, if those are similar protons on the other
Oh, no, that's a good point actually,
might
yeah.
suggest you've got average of spinning in there, which is odd to me because I'd be expecting a salt bridge between the carboxylates.
I was
and
expecting
the
something here as well, but I'm wondering if the binding here holds it in place and that binding is secondary to the intermolecular binding that we're seeing, as opposed to having this binding first and then this being the secondary binding, if that makes sense.
Depending on how much faith you want to put in simulations, that type of thing it will form transient interactions, but it won't be so stable as to be really long salt bridge, like never breaking type of thing. It'll spin around in the cavity on a nanosecond scale.
Sounds like good fodder for some simulations.
Thank you, Pip. The only other thing I should mention about NMR with cyclodextrins, we're doing everything in 10% D2O. D2O will exchange with labile protons, so we lose all the OH and NHs, which also means you lose all the hydrogen bonding, which is unfortunate. If I was to change solvents, we might be able to see it, but I can't say they would definitely get the same binding if I change solvents. So we'd need to use something like acetone or something like that, and then we might not get the solubility as well. So obviously not DMSO because that reduces binding too much. We did ITC with this as well. So what we can see is this is, just to be clear, this is data that Sam collected in PBS buffer. All the stuff I'm doing is phosphate buffer, and I'm working on repeating his work in the other buffer. Just to reduce the concentration of salts and everything else that's in there. So we're going to do this from there. So what you can see is, despite the difference in buffers, you do get a slightly decreased binding with this, but we do seem to have a certain directional binding, which at least shows us that we can use the functionalities that we're adding to the cyclodextrin to see different types of interactions occurring, which is nice. Oh, and this step here is a change in the injection volume halfway through in order to be able to see the entire curve. Yeah, these compounds are going to be quite some method development on the ITC to get them to work. But the good thing is that, like I said, we don't have any solubility issues with it, which means that we have a lot more flexibility with how we run the ITC data.
Is it the romantidine that's the solubility is limiting?
The romantin is incredibly soluble.
Incredibly
I've had no
soluble,
problems
okay.
with that. Yeah, I think I got this one up to, I think I ran this at, I got it up to 50 millimole. I didn't do that one in the end, but when I was doing it, yeah, it's incredible. We may have some issues with the other guest molecules along the way, so it's nice that we hopefully won't have a limiting factor with the host molecule, and then we only have to deal with the limiting factor with the guest molecule, which is nice.
Katie, your binding is going down when you form the salt bridge?
See, I'm not, yeah, so that's one thing, I'm not convinced it's a salt bridge. I think it's just that, if you look at the interaction.
Simulations, it's not forming a salt bridge.
Yes,
at all.
that's just that's a CH with another CH. It's not a hydrogen bond or anything like that. That's just, yeah.
So no salt bridge, you have the carboxylate
I
right
know.
beside the ammonium.
It's surprising, isn't it? But
I
like I said, I
haven't
can't
done
see
this
hydrogen
exact
bonding, so I
one,
can't
but
say.
I've done similar ones, and there's just some steric stuff that it can't quite get in a perfect position. But even if it did, at least in simulations, I'm not convinced that it'd form a long-term salt bridge.
Hopefully, the more
There's
host
so many
molecules we have.
hydroxyls around there, and those hydroxyls recruit additional ions, and it creates a whole little web of alternate interactions.
It's very interesting.
Yeah, what will be nice is to have some guest molecules that are coming further out of the cavity to get some binding with the functionalities that are going to be there, and hopefully we'll see a difference in those.
One of the things that we thought about, I mean, I don't know how baroque we want to get, but in principle we could functionalize like the ranitidine itself, you could imagine
Oh yeah.
put a little peptide there, put a little
Mhm.
peptide on the host, and
Yeah.
just really have control of both sides.
The only
of
problem I
binding
found with that
reaction.
so far is I managed to make a few, and every single one of them is completely insoluble in
Yeah.
water. As soon as you start functionalizing, so this itself, the animantane is not very soluble. I tried putting fluorescein here just because I thought, that could be interesting. Yeah, completely insoluble in water. So it's definitely something it'd be interesting to look at because then we know we definitely held that binding inside the cavity, which would be nice.
Could you remind me how you get the concentrations accurate to 1 part in 1,000? Because
To actually making up the solutions.
to be reporting an error bar of 0.01 kcal per mole or 0.02 for a delta H.
No, that's not right. It's probably coming out of origin, and it's not.
Oh, yeah, this is-
Because
I-
you need concentrations accurate to 1 part in 1,000.
No, you're right. It's not realistic.
Yeah, no, this is something that we
Just the
definitely
Okay.
it's slightly raw.
All right.
Yeah. Oh, I was going to sit down and work out how we're gonna report this properly,
Origin is over optimistic.
Yes. Yes.
which is nice, but not accurate. It's nice to have some optimism in that. So this is something. This is the last slide, but it's just an experiment that we've been working on, which is quite interesting. This is an experiment called DOSY, so it's a diffusion order spectroscopy. If you've never heard of it before, and basically the idea of it will give you the diffusion constant for your molecule, and the reason this is useful for cyclodextrins in particular is you'll be able to see aggregates because the aggregates are obviously going to move a lot slower than the monomer. So what we can see here, just as proof of principle, here is the compound I've been talking about with that succinic anhydride, and this is beta-cyclodextrin. So it's all along the horizontal axis. So everything along the horizontal axis will have the same diffusion constant. So you see a slight change in diffusion, but not big enough that you're showing any level of aggregation. So we can do these experiments to make sure that molecules aren't aggregating before we start running any of the measurements.
You've actually got this. I'm going to put words in your mouth, but she actually linked two beta-cyclodextrins together covalently,
So
and
you
you
can
can
see
see
what
the
the-
diffusion constant drop.
Yeah.
So that
Yeah.
gives sort of where you'd expect to go
Yeah.
if you were roughly if you're
Yeah.
aggregating, if
Yeah.
you're dimerizing. I don't
Yeah.
know where that would be on here, but
I reran this because I wanted to show two on the same spectrum, and I realized I ran them all separately, and it made no sense people just staring at two different spectra. So I ran this yesterday to actually just show two on the same one. But yeah, when we did the, it was actually an alpha dimer because it's what I had left.
Okay.
So we managed to make the alpha dimer linked by the succinic anhydride and then amide coupled to that amine. So you get a nice dimer, and you run that against alpha cyclodextrin, you can see a nice difference so you can definitely see it. So this should just be useful in just characterizing all of our host molecules before we start, since we know that they have the chance to aggregate. Hopefully, not hopefully, I will probably manage to make one that does aggregate soon, and then I will be able to see it on the nosy, but we haven't had that problem yet. Oh yeah, that's it. Yeah.
Anything else before we break for stretching or whatever? I don't know if there's still coffee in the back. All right, let's break for about 20 minutes.
That's good.